In the first part of this tutorial, we looked at what induction is, how it works, and how it can be used to prove a simple identity involving the natural numbers. In this second part, we'll look at some further examples of situations where induction can be useful. So far we've proved this formula here, and there are many other properties of the natural numbers that you can try to prove if you want a bit more practice. For example, there's a well-known formula for the sum of the first n squared natural numbers, which is this one here. There's also an interesting result which says that if you add together the first n odd natural numbers, the total is n squared, and that's another one you can prove by induction. And there are many other formulas involving summations, and this one here is just one more example. And the proofs of all of these results work in a very similar way to the one that we've already seen. So you start off by checking the base step when n equals 1, and then you try to prove the inductive step, which just involves doing a bit of algebra. And remember that the most important step is to try to use your inductive assumption somewhere. You've got to try to use your inductive assumption, otherwise there's no point in trying to do a proof by induction in the first place. So remember that when you're trying to do the inductive step, you need to look for a way to use your inductive assumption. So now here's another example. It's slightly different this time, and this time we have an inequality instead of an equality. And we have to start by working out which values of n this inequality holds for. And then we have to prove our answer using induction. So the inequality says that 2 to the power n is smaller than n factorial. And just as a reminder, n factorial is defined as the product of the first n natural numbers. So to start off, let Pn be the propositional statement that 2 to the power n is smaller than n factorial, and let's just try some specific values of n to see what happens if n is a small number. If n equals 1, then 2 to the power n is 2 and n factorial is 1. So in fact, the statement doesn't hold when n equals 1. And similarly, you can check that the statement doesn't hold when n equals 2, and it doesn't hold when n equals 3 either. However, when n equals 4, 2 to the power 4 is 16 and 4 factorial is 24. So in this case the statement does hold, because 2 to the power n is smaller than n factorial. And if you try some more values of n, you find that the statement also holds for n equals 5, n equals 6 and n equals 7. So our statement Pn is true for these values of n here. And if you have a look at the values that we're getting, it certainly looks as if n factorial is increasing at a much faster rate than 2 to the power n, as n gets larger and larger. So on this evidence, it looks as if our statement is true whenever n is greater than or equal to 4. But we haven't proved this yet. At this stage it's only a guess. So we're going to try and prove that our guess is correct by using induction. To start off, we have the base step. In this case, the base step is to show that the statement holds when n equals 4, because we're not trying to show that our statement is true for all natural numbers. We're only trying to show that it's true when n is greater than or equal to 4. And in fact, we already checked this earlier, so we know that the statement holds when n equals 4, and so that's the base step done. Now in step 2, we make the assumption that the statement is true when n equals k. So we assume that 2 to the power k is smaller than k factorial, where k is greater than or equal to 4. And we need to show that our statement is true when n equals k plus 1. So in other words, we need to show that 2 to the power k plus 1 is smaller than k plus 1 factorial. And in fact, we can do this quite easily. First of all, we say that 2 to the power k plus 1 is equal to 2 times 2 to the power k, using the rules of indices, and then we bring in our inductive assumption, which is really the critical step, and say that 2 to the power k is smaller than k factorial. And we can say that 2 times k factorial is smaller than k plus 1 times k factorial, because remember k has to be a number greater than or equal to 4. And using the definition of the factorial, we can say that k plus 1 times k factorial is equal to k plus 1 factorial. So in summary, we've shown that 2 to the power 4 is smaller than 4 factorial, which is the base step, and we've shown that if 2 to the power k is smaller than k factorial, then 2 to the power k plus 1 is smaller than k plus 1 factorial, which is the inductive step. And that's enough to prove that 2 to the power n is smaller than n factorial whenever n is greater than or equal to 4. So to finish off, we're going to look at a slightly different type of induction. Suppose we have a statement which depends on more than one variable. For example, let p n1 n2 be a statement which depends on n1 and n2. So we're now considering a two-dimensional case. The question is, how can we use induction to prove our statement is true for any pair of natural numbers? Well, first of all, we have the base step. In this case, we have to prove the statement is true when n1 equals 1 and n2 equals 1. So in other words, we have to prove that p11 is true. Secondly, we have the inductive step. In this case, we have to make the assumption that p k1 k2 is true, where k1 and k2 are fixed natural numbers. And then we have two things to prove. We need to show that the statement holds when the value of k1 increases by 1, and we also need to show that the statement holds when the value of k2 increases by 1. So let's very quickly look at why this works. If we've done the base step, so we know p11 is true, then we can use the inductive step to say that p21 and p12 are true, since we can get to both of those statements by increasing the values of n1 and n2 respectively by 1. And then by using the inductive step again, we can say that p31, p22 and p13 are also true. And you can see how we can keep this argument going, and for any pair of natural numbers n1 and n2, we'll be able to prove that pn1 n2 is true, simply by applying the inductive step enough times. So let's just summarize what we've talked about in this tutorial. You can use mathematical induction to prove that an infinite sequence of statements must all be true. So a typical situation where we would use induction is if we wanted to prove that a statement involving n was true for all natural numbers n, or if we wanted to show that a statement was true for all natural numbers greater than a certain value, or if we wanted to show that a statement was true for all pairs of natural numbers, for example. The base step involves showing that the first statement in the sequence is true, and the inductive step involves showing that if one statement is true, then the following statement is true. And that's really all there is to it, because if we've carried out these two steps, we can use the so-called domino effect to conclude that all of the statements in the infinite list must be true. So induction is really a very simple but also a very powerful technique, and it's important to recognize when we can use it effectively. Thanks for watching this tutorial, and look out for the next one coming soon.